Hello all. In this video, we'll learn about asymptotic notation. First, we'll look into the definition of asymptotic notation. So, asymptotic notation is a mathematical tool used to describe the efficiency of an algorithm. Sorry, efficiency of an algorithm in terms of time, space, or as the input grows towards infinity. It helps us analyze the upper, lower, or tight or average bounds of an algorithm's performance. So, diving into deep, asymptotic notation is nothing but a mathematical way to describe how an algorithm time or memory usage increases as the input size grows. So, how algorithms time, memory, memory usage grows or increases as input size grows. So this is what deals with asymptotic notation. In simple terms, it helps us understand how fast or slow an algorithm will be, especially when dealing with large amounts of data. How the algorithm works fast or slow when there is huge amount of input data. So this is how asymptotic notation works. So basically there are three primary asymptotic notations that are big O, omega and theta. Big O deals with upper bound, worst case, and omega deals with lower bound, best case, and theta tight bound or average case. In this video, we will mainly focus on the worst case or the upper bound big O notation. Big O notation shows the worst case time or space. It deals with both time and space. Time and space requirement of an algorithm grows as the input size increases. So using big O notation, we'll read how the time and space increases or the requirement goes on as the input size is growing. It helps us compare different algorithms without worrying about the hardware or programming languages. So there is no need to worry about programming language and hardware. We can compare the algorithms. So, in detail explanation of big O notation is that it provides a worst case time or space complexity of the algorithm, as already we have discussed. Big O notation provides the worst case time and space complexity of an algorithm. It describes how the runtime grows relative to the input size n. So, how the runtime increases relative to the input size increments while ignoring lower order terms and constant factors. Okay. So coming into the basic definition, a function f of n is O of g of n if there exist positive constants c and n0 such that for all n greater than or equal to n0 and f of n less than or equal to c into g of n. We will learn about this. So a function f of n is O of g of n if there are constants c and n0 such that for every input size n greater than n0, f of n is less than or equal to c times g of n. In simple words, big O gives an upper limit on how much time or memory an algorithm might take. So, in simple terms, what is all this definition tells about is that big O gives an upper limit. So, big O gives an upper limit on how much time or memory an algorithm might take. Okay. About the time or memory an algorithm takes, big O notation makes the estimation. So why using big O notation? Compare how efficient different algorithms are. So to compare the efficiency of the algorithms, different algorithms, understand how they behave as input gets larger, to understand how algorithms scale up or down with larger inputs or lesser inputs, and focus on the most important part of the algorithm's growth, ignoring smaller terms and constants. To focus on dominant terms, we will not consider constants or less significant parts. Let's look at some big O complexities. We have discussed this also in the last video. O of 1 is named as constant. The time stays the same no matter what the input size is. So the time remains the same no matter what the input size is. Time does not grow with the input size. Example, accessing array elements. Next one is O of log n, that is named as logarithmic time. Logarithmic time. The time grows slowly, often used in divide and conquer algorithms. Input shrinks by each step. Input shrinks half by each step. Time grows slowly, and time grows slowly as the input size increases. So the example is binary search. O of n is linear time, grows proportionately to the input, that is time grows directly with the input size. As the time increases, as the input size increases, time also increases. Linear search is the example. O of n log n, that is log linear time, faster than quadratic, common in efficient sorting algorithms. This is faster than quadratic, that is O of n square. It is very common and efficient in sorting algorithms. So examples are merge sort and quick sort. O of n square, quadratic time. Time grows quickly, often seen with nested loops. So as the input grows, time also grows quickly. Time grows quickly. This uses nested loops over inputs. So one of the famous example is bubble sort here. Exponential or factorial time, that is O of 2 to the power of n or O of n factorial. This grows very fast. These are not practical for large inputs. So these are not at all recommended for larger inputs. These are not practical or recommended for larger inputs. No. So recursives and permutations and combinations are the examples of exponential and factorial complexities. These we have explained very detailed in the last video. So one example of constant time is that the time does not grow with the input size, is that just returns the first item from an array. This function returns first element or item from an array. This function get function array of 0 positions. So it just returns the first element from an array. This is an example of constant. So this will not take much time. And linear time example, it prints every item. Time depends on the number of the elements. So this example print all is printing each and every element of an array. So grows proportionately to the input. If input is 1, time taken is almost same to constant time. If the input is 5, the time increases. If the input is n, also the time increases more proportionately to the input. Next is quadratic time. As we have already discussed, quadratic time deals with nested loops. This is the first loop and this is the second loop. The number of operations grows faster as the input gets bigger here. So the number of operations, initially the operation in the first loop is n and in the second loop is also n. So n into n becomes the quadratic equation as we have discussed here, O of n square. O of n square. So the number of operations multiplies or grows faster as the input becomes bigger. So finally, big O ignores constants and focuses only on the most important terms or the dominant terms. It does not depend on the hardware or programming language, as we have already discussed. Big O notation does not depend on the hardware or language, programming language. Constants are ignored. We use big O to focus on long-term behavior of the algorithm as the input grows. So using big O notation, what are we doing? We are focusing on long-term behavior of an algorithm. Long-term behavior of an algorithm. To sum up, big O notation helps us describe the worst case performance of the algorithm because it sums up and binds the upper case of the maximum time or space taken by the algorithm, as we have already discussed by the definition. Big O notation estimates on the upper bound of maximum time or space taken by the algorithm. So it describes the worst case performance of the algorithm. It helps evaluate scalability and choose for better algorithms. It is a powerful tool for comparing and choosing the most efficient algorithm. Understanding big O is essential for writing faster and scalable code. So we can write problem solving and software designing also using big O notation. Thank you.